Shalom and welcome back, everybody. We are going to change direction in terms of where we point our instrument to. So this session is called Looking into Space, and the idea is to talk about basic research, basic astronomy, using satellites. And we are going to do it in a somewhat different way because we want to emphasize two things. First of all, 3 new missions, and secondly, missions that Israel is involved in. And the missions will be introduced by 3 teams, 2 teams and one individual. And the first one is called JUICE. I probably not pronounce it correctly, but this is the idea. The idea is to send something to Jupiter, and it's going to be introduced by 2 co-PIs, one from Italy and one from Israel. The one from Italy is Professor Luciano, and he's at the University of Rome, and he's got very rich experience in space mission, many of them in the solar system, and he is the PI of this experiment, and he will tell us when it's going to be launched. The other one is Professor Yוחאי Kesfy from the Wisman Institute of Science. Yוחאי got his degree and experience in the United States, MIT and then Caltech, and now he's in the Wisman Institute, who, as you know, devote a lot of effort into studying the solar system, and they will introduce the topic together. So, Professor, yes?
Thank you, but I need the tiny device which allows me to advance. Anyway, I'm here to present the collaboration on the JUICE mission, and I'm honored to be here because this is an opportunity for Europe to expand the range of countries with which it has scientific collaborations. Israel has a very lively space industry, and it's a pleasure that this collaboration that is already going on other missions is taking place also on the scientific program. So, JUICE is a name. It was supposed to be a placeholder. It's a name that I don't like much. A placeholder for something that should have been changed later, and probably there will be an announcement also for a different name, but it stands essentially for Jupiter Moons Explorer. And the main focus of this mission is indeed the Jovian system. So Yוחאי is a friend and a colleague of me. We are collaborating since a long time, also on other missions, Juno and Cassini as well. And now we are starting this new idea, new experiment at Jupiter. So the team is an international team made up by many scientists from Italy, Israel, European countries, and the US. And Yוחאי is a co-principal investigator. The hardware is procured by 2 space agencies, the Italian Space Agency and the Israeli Space Agency. The whole mission is managed by ESA. A few words on the background themes and topics of this mission, and they are really overarching topics because in the end, JUICE will give a contribution to understand the habitability of outer moons, the moons of the outer solar system. We know that liquid water, which is an essential ingredient to life, does not exist only in the zone which comprises the Earth. But there are deep habitats in the solar system that have been recently discovered where liquid water is abundant. And therefore, it's essential, it's very important to understand how these habitats, to characterize these habitats. And they are in the Jovian system and the Saturn system. So what you see here are the Galilean moons of Jupiter and 2 of the moons of Saturn, Enceladus and Titan, not to scale because Enceladus is very tiny, 250 kilometers. Titan is 10 times bigger in radius, where liquid water exists. We know that on Enceladus you see the jets, the geysers coming out from the South Pole of this tiny moon, very active. Liquid water is abundant there. And the same is true on Titan, because we measure tides on Titan with the Cassini mission. In the Jovian system, we know that Europa certainly hosts a deep-seated ocean at a depth which can go from 1 kilometer to 50 kilometers, so something which is in reach of possible future exploration, so something very interesting. And the mission JUICE will go to the Galilean moons, especially Ganymede, Europa, and Callisto, and will land in orbit around Ganymede. It will be the first orbiter of an icy moon of the solar system. So the themes that this mission will address relate to habitability. And in order to understand habitability, it's crucial to know what's inside, what is the interior structure of these bodies. Essentially, JUICE will do a tomography of Ganymede and will gather a lot more information on Callisto and Europa as well. And the tomography of Ganymede will be made by certain instruments, and 3GM that Yoai and I are leading is one of these. It's an instrument which allows to peek inside the moon. We have seen these beautiful images. Most of past exploration of the solar system was devoted to understanding surfaces and atmospheres. But understanding what's inside is much more complicated and difficult. We don't have seismic prospection, for example. We don't have a network of seismometers on other bodies. So we have to rely on long-range forces and indirect information, and gravity certainly is one of these. The other important instrument to understand the interior of these bodies is the laser altimeter, and also magnetic fields provide information. Of course, JUICE will not only go to Jupiter to study the moons, but also to study Jupiter itself, and Yoai will talk about this later. So there is, the mission will be launched in 2022. We are currently between phase B and phase C. We have the ICDR of our instrument, which I will describe later in a couple of months. So we are in a critical phase of the mission. Launch in 2022, arrival at Jupiter after 8 years in 2030, and then we will start a tour of the Jupiter system with many flybys of Callisto and 2 flybys of Europa. And then we will end up at 500 kilometers and perhaps 200 kilometers altitude orbit around Ganymede. The instruments that are on board are very diverse. As I said, there are 3 of them which are focused on the interior structure of the moons. And these are a laser altimeter provided by DLR, a magnetometer provided by the UK Space Agency, and finally 3GM, which is provided jointly by the Italian Space Agency, which is also the lead funding agency, and the Israeli Space Agency. So the instruments that we will place on board in order to carry out this tomography of Ganymede and the moons is the KAT, is a transponder, very accurate star transponder, capable in principle to enable range rate measurements of the spacecraft, essentially the spacecraft velocity at 3 microns per second. Actually, the instrument can do 10 times better than that. And is a heritage from a similar instrument built on Bepi Colombo, and it's a very rather mature instrument. And then we have an Israeli contribution, the ultra-stable oscillator, which will be used to carry out occultation, radio occultations of the Jupiter atmosphere. So these are the two pillars of our experiment. As far as I know, the USO will be the first Israeli piece of hardware, instrument actually, not piece of hardware, but instrument flying to the outer solar system and leave the Earth orbit. And this is remarkable. I'm proud to have favored this event. Just a final slide to let you know how we think we will be able to determine the interior structure of Ganymede. As I said, gravity is a long-range force, so in principle, by measuring how the JUICE spacecraft will fall into the gravity field of the moons, will provide information about the interior structure. There is no instrument that can measure gravity in space. If you put an accelerometer, it will measure a zero. Actually, it will measure everything but gravity, non-gravitational accelerations. So every gravity measurement in space must be differential. And here the two end bodies are the Earth, a ground station, and the JUICE spacecraft that is flying into the gravity field of Ganymede. So we will measure the relative velocity between these 2 points with an accuracy, as I said, of about 3 microns per second. And 3 microns per second is indeed a lot less than the speed of the snail. And by measuring gravity with such an accuracy, indeed, this means that we will be sensitive to the tiny and fine structure of the density anomalies inside Ganymede. So unfortunately, this will take place in 2033 when JUICE will enter orbit around Ganymede, but we will do measurements already starting 2030. Unfortunately, planetary exploration requires a lot of patience. We all know that, and I hope to be fit to see the end of that mission. Thank you. And now let me introduce also Yoi, who will talk about the second part of the 3GM experiment.
Thank you, Luciano. So Luciano talked about JUICE in general and about the isosatellite part of JUICE, the objectives for that. And I'll turn and talk about the scientific objectives for the atmospheric dynamics of Jupiter itself, an experiment that we will be doing in parallel to the experiments of the isosatellites. Let's see. So Jupiter's atmosphere is very dynamic, as you can see here in these pictures going back to the Voyager mission almost 40 years ago. You can see the very strong eastward flow at the equator, the superrotation. We have 6 jet streams in each hemisphere, more or less. A lot of turbulence. You can see, of course, the great red spot, the famous vortex in the southern hemisphere, and all the structure there's around that. But despite having a lot of data in the past 40 years, both from spacecraft and also just from Earth observations, we have known very little about what's going underneath this cloud layer of Jupiter. And this was, as I said, for the past 40 years until a year and a half ago when the Juno mission arrived at Jupiter. And Juno and JUICE are somewhat complementary missions looking at different parts of the atmosphere, and I'll talk about that. And Juno really revolutionized the way we think about Jupiter. Also, this collaboration between Luciano and myself began with Juno and is ongoing for the past 10 years, and we're now carrying this on into the JUICE mission. So the reason I'm saying it's complementary, because with Juno, we're measuring the gravity field through measuring gravity, and through that we're looking at mass anomalies within the planet. When we're trying to measure mass, of course, we get more weight as we go down, where there is more mass in the atmosphere, and therefore we're able to look at the bulk atmosphere, how deep it is, etc. I'll go over that in a minute. While with JUICE, we're doing occultation measurements of the upper atmosphere. So we're probing very different regions of the atmosphere, and therefore it becomes, these put together will give us a 3D map of Jupiter's atmosphere when the time comes, of course. So a little bit about Juno, and I want to emphasize how much we learned just over the past year about Jupiter. So Juno is orbiting Jupiter every 53 days in an orbit like you see over here. So it's a very eccentric orbit. It's a polar orbit. And every 53 days we go around and have this perijove, meaning we get very close, about 4,000 kilometers above the cloud level of the planet. And to remind you, the radius is about 70,000 kilometers, so really very, very close, much closer than any other spacecraft in history. And our next perijove is just coming up next week. It's going to be the 11th time we go around Jupiter. And just to give you a sense of how this looks from sitting on the spacecraft, then this is a movie of Juno coming in from pole to pole. It takes us about 2 hours to do this pole-to-pole maneuver. One thing that we learned is that the poles of Jupiter have a lot of vortices, which you see there close to the terminator. The terminator is roughly at the pole. And as we get close to lower latitude, we go from this region of vortices to a region which is dominated by jet streams that you see over here. We're now approaching the equator of Jupiter. And then we're going to exit from the south side. This is the Great Red Spot. We just passed over it. And now we're exiting from the southern hemisphere of Jupiter. And you can see all this structure in this, in the atmosphere here. I'll let you just enjoy the pictures for a second. And then we see the views of the southern hemisphere, which is dominated also by vortices with somewhat of a different structure than we see in the northern hemisphere. Okay, and so we're repeating this thing every 53 days, and we do it on different longitudes. So at the end, after 30-something orbits, we're going to have a 3D picture of Jupiter in this sense. And like I said, we're probing deep into the atmosphere with looking on gravity measurements. So what did we learn over the past year with this? The first thing that we learned is that Jupiter's gravity field is north-south asymmetric. If you just think about a rotating gas planet in space, it should not have a difference between north and south in its gravity field. But the winds, like you saw before, which you can see also here, you can see I can point at this. Well, okay, so I have the pointer. You can see that the wind structure is asymmetric between north and south here. So that creates a difference in the gravity field between north and south. And the winds are deep enough so we can use this difference in the gravity field to actually know how deep the jet streams are going. So if before we did not know how far what we were looking from the outside is going, now we know that these are 3,000 kilometers deep. So it's a very deep atmosphere. In the sense of looking at the whole planet, you can see it's only 3,000 out of 70,000. But in terms of an atmosphere, we have an atmosphere going down to 100,000 bar, more or less. Or in other words, it contains about 1% of the planet. So 1% of the planet of the mass of the planet are these flows that you saw in the movie before. We also know that it goes down roughly to where it begins to interact with the magnetic field. So the magnetic field begins to be dominant in terms of dissipation of the flow at about 3,000 kilometers deep. You can see the profile over there. This is a profile that we were able to deduce just from these gravity measurements. And interaction with the magnetic field is what damps down the atmosphere at those levels. Below that, the planet is nearly rotating as a rigid body. We know now that there are no deep flows in the deep interior of Jupiter. And we also know that the core in the interior is likely bigger than what we thought before. But it's not a solid core, as we were used to think before, but it's more of what we call sometimes a fuzzy core, or something that is interacting more smoothly with what's happening above. We're still studying this. All this is just from the past year. Especially the issue of the core is very much a subject of study, but just thought it's going to be interesting to show you where we are in the study of Jupiter dynamics. And this is really all something that's all coming out. Some of this has not been even published in the past, and it's going to be coming up in the next few months. So now going back to JUICE. All what I described now is just looking deep into the atmosphere and how it deeps and how it interacts with the magnetic field. The forcing of the atmosphere, the reason that you see these jets on the outside is coming from turbulence at the outer level. So we really want to be able to probe that, and that we cannot do with gravity. For that, we're going to be doing the JUICE occultation experiments. So what you see over there is kind of a diagram of what we're going to be doing. We're going to be sending a radio signal through the atmosphere down to the ground station. And because of the complicated orbit of JUICE, because it's going to be flying by all the isosatellites, so the orbit is not going to be a standard orbit, it's going to be basically going around the planet at all different latitudes and longitudes. So that gives us a 3D map of Jupiter's atmosphere if we can probe it at each one of these opportunities. We're going to be trying to do that. And the experiment is basically, in very simple words, is this. When we send a beam from the spacecraft to Earth, if it's going through the atmosphere, then it's attenuated because it's going through a different medium. And if we have a very accurate measurement of time on the spacecraft, we can now track that attenuation of the beam, looking at the frequency shift, and therefore probe the atmosphere of Jupiter at many different places around the planet. So to do that, we are developing here in Israel the Auto-Save Oscillator. This is going to give us a very accurate measurement of time. It's developed by the Israeli company AccuBeat, and the accuracy is going to be several 10 to the minus 13 of a second over a time interval of 1 to 1,000 seconds. And we're in a very advanced stage now of preparation. We're going to be delivering the instrument to ESA, the European Space Agency, in 2019, the end of next year. And launch, as Luciano mentioned, is planned for 2022, and then 8 years in cruise until we begin the occultations in the middle of 2030. This here is an image of the instrument itself, this box that's being developed by AccuBeat. This, if you can see, this is a graph of the frequency stability. This very, very accurate up to 1,000 seconds. And I'll just conclude by saying that this is a remarkable opportunity for a collaboration between the academia, the industry, and the space agency. As I mentioned, AccuBeat are leading the development of the instrument. Us at the Weizmann Institute, we're doing the science, and we're going to be doing the analysis of the data when it's arrived, and we're now preparing the machinery in order to be able to do that in terms of software, et cetera. And of course, this is led and managed and funded by the Israeli Space Agency, and we owe a great courtesy for them for carrying on this project and leading it. Thank you.